Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video we're going to be exploring a really very interesting topic, which is actually called mean free path. Mean free path is quite different, of course, from our collision frequency, which we talked about on our previous video. Collision frequency actually is important in terms of determining how many molecules are actually being collided by one particle. And so we have a little illustration where we are given a specific tube, and based on the tube, which is actually called the collision tube, various variables were considered, like for example the area, which is the cross-sectional area of the tube, represented as this particular symbol, and this symbol is actually equal to the pi d squared, where d is actually the diameter of our specific molecule that is passing through this particular tube, and the diameter is actually equal to the radius. So r is equal to d, and since we have this taken into consideration, our next variable that we need to consider is the path that it takes, which is all the way to the very end of the tube, where the specific distance is expressed as our relative mean speed multiplied by our time. And so once we have this taken care of, our next thing we need to take into consideration is the collision path. Is it going to collide with this particular particle, which in this case is represented as heat, where we express this as A, or it's actually missing or misses a specific particle, which is expressed as B, and this particle here is called a miss during when this particular particle is moving through this particular tube. So based on these particular assumptions, we were able to come up with the conclusion that by showing the relationship between not only the number density, which is represented as this particular weird n, and weird n is actually using the number of particles, which is A, and that of the volume of this particular system, but also the specific cross-sectional area, and as a result of that we are able to combine this with the specific relative mean speed. So relative mean speed is actually known to be the square root of 8 multiplied by RT over pi m, and we know that the number of particles is actually related to the number of moles, and we know that the number of moles in this particular case is linked really well to the particular equation, which is PV equals nRT. And in this path we also know that RK, which is known to be called the Boltzmann's constant, is related in terms of the specific gas constant and also that of our specific number of particles, which is Na. So all these little variations and variables were taken into consideration to determine our collision frequency. And our collision frequency is, in summary, when you introduce all these variables in, we actually arrive at an expression which is represented as the pressure divided by our Boltzmann constant, and this is multiplied at the denominator by the specific variable, which is called the temperature, and this is all multiplied by our cross-sectional area. And finally we know that this is linked to the relative speed of our specific molecule, relative mean speed. So once you have this taken care of, this is actually a summary of what we did in our previous video. And on our video today, based on this particular question, we are actually going to calculate the mean free path. And the mean free path is an interesting term of carbon dioxide molecule using the cross-sectional area, which in this case is represented as this, to be equal to 0.52 nanometer squared, and at a specific temperature where this particular tube temperature is equal to 25 degrees Celsius, and finally it's having a pressure to be around 15 atmosphere. So couple of units will be converted into standard units that highly links to one, the Z value, and also how the Z value, which is collision frequency, links really well to the mean free path. And how does this relationship plays out? The mean free path is known to be called the distance between one particle before it hits a specific particle in space. So therefore, the distance that is actually made during this particular trip is expressed as a specific conversion. It's actually expressed in this case as lambda, and lambda, which is the mean free path, is equal to 1 over our specific Z value. But take note here that this particular expression is represented as the time spent in the free flight between collision. So once we have this time expressed as 1 over Z, which in this case Z is the frequency which is collision wise, we also need to take note that since we're determining distance, which is represented as lambda, distance is the time multiplied by the velocity, and in this case our velocity will be using the specific mean speed. And so therefore, once we have this expression taken care of for determining the mean free path, we can then introduce other variables into this particular expression to create a new expression that would then result in our determining of our final answer. And so once we have this taken care of, we're going to go really deep into analyzing this particular question. Take note that based on the expression for our lambda, which is equal to the specific mean speed multiplied by 1 over Z, we know that by combining the following equations, which is 1, where our Z is equal to, based on our previous video, the pressure divided by our Boltzmann constant multiplied by the temperature, and this is all multiplied by our specific cross-sectional area and the relative mean speed. This relative mean speed is expressed as the following, which is square root 2 multiplied by our mean speed. Therefore, when we put these two equations here in this particular equation, we'll be able to determine our new expression, which is the mean free path. And so therefore our mean free path is actually equal to the Boltzmann's constant multiplied by temperature, all divided by our pressure and multiplied by our cross-sectional area, and this is multiplied by square root of 2. So we have our new equation, and this new equation will be used in this particular problem. Therefore, looking at our specific givens, we need to now look at how this is applicable to the conditions and what are the things that actually really relates really well to this problem. One is the consequence is if you double the specific pressure, we automatically have our specific individual mean free path. And so therefore this actually shows that, hey, in applications when you have nitrogen gas at 1 atmosphere, the mean free path is actually 70 nanometers, which is around 10 to the 3 molecular diameter. And this is really small and interesting to see how little distance is required for one particle to collide with other particle at 1 atmosphere. And so take note here that this particular lambda, which is the mean free path, is actually not dependent on the temperature, because since the mean free path is fixed at the volume, we see that since the temperature is directly proportional to the pressure, the ratio of the temperature and pressure, though increasing, remains constant at that particular rate when it's related to our mean free path right here. So it's really interesting to have these actually taken care of and put at the back of your mind when dealing with problems in here. So in this particular video, we're going to now solve the problem, and by solving the problem, we'll be able to analyze this particular question. So therefore, based on the question, we are looking at the givens, which includes the following. We have molecular weight, that is, if that will be considered in this question to be, in this case, for carbon dioxide, we know that carbon is 12.01 multiplied by, well, 1, of course, because there's just 1 of carbon, plus oxygen, which is 15.99, and this is multiplied by 2. And so therefore, this is going to be measured in grams per mole, which is around, in this case, 43.99 grams per mole. Take note that in terms of our units for the Z value, which is the collision frequency, our gram per mole, which is going very heavily on the specific C bar, which is the mean free path, actually links the units to be in kilograms per mole. So therefore, converting this to kilograms per mole, it means that we're going to multiply by 10 to the power of -3, which means that our new value will be 43.99 times 10 to the power of -3 kilograms per mole. So that is one thing to take care of. Now the next one here, based on the question, is the pressure, and the pressure here is given to be 15 atmospheres. Now we need to convert this to our specific kilopascal. So what is kilopascal when the atmosphere is 15? So in this part here, we know that 1 atmosphere is equal to 101,325 pascals. Therefore, for 15 atmosphere, we need to multiply 15 by this particular 101,325 pascals. Therefore, our value now is 1519875 pascal, or in this case we have 1519.875 kilopascals. So that is one thing to keep in mind in here. We need to change our units in here to pascals instead of using atmospheres, because we're going to be borrowing heavily on the constant for the Boltzmanns and also the R value. So next one here is looking at our specific cross-sectional area. Given this question is 0.52 nanometers squared. Take note, we need to convert this to, in this case, meter squared. Therefore, since we know that one particular value for meter squared is equal to 10 to the -18 nanometer squared, therefore, in this case, 0.5 nanometer squared means that we are going to be playing with, oh no, I made a mistake. Since we know that in this case for nanometers we need 10 to the power of 8 nanometers, 18 nanometers squared to get to 1 meter squared. Therefore, in this case, for 0.5 2 nanometers squared, we're going to divide 0.52 by 10 to the power of 18 nanometers. Therefore, we're going to have our value to be 0.52 times 10 to the negative 18 nanometer, meters squared. So this is going to be used in this particular question as well when dealing with the cross-sectional area. And then the next one here is looking at, hey, how are we going to convert any other thing else? Now we know that the temperature is given to be equal to 25 degrees Celsius, which means that we need to convert this to kelvins. Therefore, convert this to kelvins means we're adding this value to 273. Therefore, we're going to get this value in kelvins to be around 298 kelvins. And so, since we know that we are required to determine the specific mean path, which is represented as lambda, and lambda is the mean path or mean free path specifically, we will then actually derive our mean free path, which we already did in this particular question. Now, based on analysis, we actually notice by analyzing that where our z is equal to square root of 16, based on our previous video, r over pi molecular weight multiplied by the temperature. All this is multiplied by our specific cross-sectional area times the pressure divided by Kelvin, the Boltzmann constant. We know that this here, we know also that our specific mean free path, our mean speed is equal to all square root of 8 RT over pi m. This actually lead us to combining those two expressions in our mean free path, which is expressed as our mean speed all multiplied by 1 over z, which is the time. And therefore, we'll be able to incorporate our k value in here, where k is equal to r over the number of particles, and this here is equal to, in this case, lambda equals to kt over pressure multiplied by our cross-sectional area multiplied by square root of 2. So we're going to use this expression, and from there on we'll be able to solve our problem. And so by solving, we're going to substitute our givens into this equation, and we'll be able to determine our solution. Take note that k, which is the Boltzmann constant, is equal to 1.38 times 10 to the negative 23 joules per kelvins. Therefore, we know that in this case, since our mean free path is equal to kt over the pressure multiplied by the cross-sectional area square root of 2, we will be able to put our numbers in, which in this case is our k value is 1.38 times 10 to the negative 23. Take note that joules is expressed as newtons times meter, and this is divided by our kelvins, and this here is multiplied by our temperature, which is 298 kelvins, and this is all divided by our pressure, which is in this case expressed as the 1519875, where the unit of pressure is actually represented as pascals. So therefore pascals is equal to newtons per meter squared. Therefore, in this case, once we have this, we would then multiply this by the cross-sectional area, which is 0.52 times 10 to the negative 18 meter squared. And take note that this is also multiplied by square root of 2. So once we have this taken care of, we will then deal with our units by cancelling out our newtons. We have our squares of the meter at the denominator cancelling out. We have our kelvins cancelling out at the numerator. And what we're left with is our meter, which rightly represents the unit for the mean free path. Therefore, by multiplying our numerator constants and dividing our answer by the product of the denominator constants, we're going to arrive at our number for the numerator to be 4.1124 times 10 to the negative 21 meters, and this is divided by our denominator, which is 1.1177 times 10 to the negative 12. And so once we have this taken care of, our mean free path is equal to 3.676 times 10 to the negative 9, which is really close to the specific magnitude of nitrogen gas at 25 degrees Celsius, which we said is around 70 nanometers. So as long as your answer is around the nanometer scale, that is really good. That is a great indication that, hey, that is the mean free path of a typical molecule in that specific temperature, though maybe different pressures depending on where you position those molecules. So really fascinating to see this play out, and this indeed tells us that, hey, the two molecules, the distance that is made by that one moving molecule as it approaches a static molecule will make a distance on average to be around 3.68 nanometers. So that is about it for this particular video. Hope you're able to understand the mean free path and how this is derived and applied to a question involving carbon dioxide. And believe me, it is applicable to all kinds of questions involving kinetic model of gases. So thanks for following me through this. Really appreciate it. Please hit a comment down below. Let me hear your thoughts about this. By the way, I can talk to you soon. Stay smart as always and believe in yourselves.